So section 6.2, what we're doing is we're getting used to what the graphs of sec, cosec and cot look like. So I think I will draw the graph of cosec because in the last video I did quite a few examples with a sec, so let's go for a cosec. So sine starts at 0 and does this. Now I'm not going to label my x-axis, and the reason for that is because this could be labelled in degrees, it could be labelled in radians, it doesn't really matter which, right? So I'm just going to leave it so that we get the general shape, and then, oh, it's a terrible one, isn't it? Sorry, it's not. It should be symmetrical about the x-axis. Let's start again. I'm just going to leave it so we get the general shape, but I'm not going to worry about whether this is 90 degrees or pi by 2. Okay, so here is my sine graph. Looks something like this. Oh, it's still pretty bad. Never mind. So, what does cosec theta look like? Well, cosec theta is 1 over sine theta. So I'll put in black sine theta equals y equals sine theta. Let's go in for red for what does cosec look like? Well, here the value of sine theta is 1. So 1 divided by 1 is 1, so it's going to be the same there. Now what happens to sine theta, and I'll just put a vertical line on here up to this point here. So if we're in radians, this is pi. If we're in degrees, this is 180. Well, as I move to the right, the value of sine gets smaller. So if I do 1 divided by that, then I'm going to get a bigger number, aren't I? And 1 divided by a smaller number and a smaller number. So by the time I get down here, I'm doing 1 divided by a very small number. So if this sine graph is getting smaller, then 1 over that, or cosec of theta, is getting bigger. So it's going to go like this. Now as sine gets down here and gets close to 0, then what's going to happen to cosec theta? Well, 1 divided by an incredibly small number is an incredibly big number. And then when I hit this point here, this pi radians or 180 degrees, I'm going to have an asymptote, aren't I? Because I can't do 1 divided by 0, so I get this sort of shape. And then I can repeat that argument over here. And the same thing happens down here, but negative, okay? So 1 divided by -1 is -1. 1 divided by a negative number smaller than -1 is a negative number bigger than -1. 1 divided by an incredibly small negative number is an incredibly big negative number. So we get this sort of shape. So these dotted lines here are the asymptotes, and the red curved shapes are what my graph of cosec theta looks like, okay? And they should be sort of touching at these turning points. So the minimum point on the cosec graph is the maximum point on the sine graph. Now if you repeat that argument, have you noticed I didn't refer at any point to where this y-axis is? So if we just cover up that y-axis, you wouldn't know if this is a sine curve or a cos curve, would you? So the graph of sec looks exactly the same, only shifted along in the same way that the graph of cos looks like the graph of sine, but shifted along, okay? It doesn't matter whether we measure it in radians or in degrees, this is the shape. So we end up with these things. Now, we then end up with a whole sort of load of bold type bullet points here with all the details in. But if you just stop and think about it, these details sort of almost don't need memorizing, because if you just think about the shape of the graph, this is the way it's got to work. So the domain of sec, well, so this is the cos one here, right? So if you imagine the cos graph, in fact, I think they do this for us on the previous page. So let's have a look. Look, here's our cos graph, and it's the same argument. We get these lumps there for the sec graph. So if we look at this, the domain of sec, well, sec is always valid apart from not at these vertical asymptotes. So the domain of sec is all real numbers, not counting if we're in degrees, 90, 270, 450, and so on. And if you're in radians, then pi by 2, 1.5 pi, 2.5 pi, and so on. So multiples of pi by 2. Odd multiples of pi by 2. The range, well, what are the values of y that this thing takes? Well, the range of cos is from -1 to 1. The range of sec is from 1 upwards and from -1 downwards. So there's 2 parts of the range like that, okay? Now the same thing is what we get here for the cosec graph, and the domain again, is fiddly to write down, but when you think about it, it's just all the real numbers, not counting these points where there are asymptotes. And the range of Cosec is less than -1 and bigger than 1. Okay, so two separate parts of the range. Now, if you do the same argument with the tan graph, and you do 1 divided by the tan graph, you end up with this shape here for the cot graph. And I suppose it is a separate shape, so you might want to pause the video and have a go at doing this one yourself. But let's just, well, in fact, what I'll do is I will ignore where the y-axis is. I'm just going to say, well, the tan graph is this shape, so what does the sec graph look like? In fact, I'll put an asymptote there. That's an asymptote on the tan graph. So the tan graph's this sort of shape. So here we get 1 divided by a very, very, very small number. So we're going to get an asymptote in here because tan is very small and getting slightly bigger. So as it's tiny, the value of cot is enormous. And then we sort of swoop down here. At the point where tan equals 1, then cot equals 1 as well, doesn't it? Okay, and if you remember, that if this was 0, this would be 45 degrees, right? So 45 degrees away from the point where it hits the axis, that's where we get our crossing point between our tan graph and our cot graph. So there's my cot graph swooping down like that. As tan gets bigger and bigger and goes to infinity, cot graph goes towards 0. And then I'm just going to miss out this point here where there is an asymptote at the moment, and then we get this again. So there's the shape of our graph. Okay. Now let's just have a look at this 0 point here. If that is a point, so say that was 90 degrees where tan is undefined, you can't have tan of 90 degrees. Well, what happens to cot? Well, I can't do 1 over an undefined number, but what I could do is say, well, to the left, it gets very, very close to 0, and there's just 1 point where it's not defined, and then to the right, it carries on from 0 and downwards. So if I just fill in that point, and I just define that cot of 90 degrees is 0, then this is a nice smooth curve, and there's not a sort of missing point in the middle. Okay, I could have this function that kind of works like this, a nice big red curve, and there's just one value there in the middle where we get 90 degrees or any other point where tan has an asymptote, and say, well, that's not defined. But what we'll actually do is we'll sort of stick it together. We'll say cot is defined as 1 over tan, and then when tan is not defined, we'll define cot as 0. Okay, and that's a perfectly good way of defining a function, and it gives us a nice smooth curve. So there's my cot graph there, and again, you get these asymptotes, so you've got to be careful with the domain. But if you think about the domain, it's going to happen. You know, the points that are not defined, you can work those ones out. The range is, in this case, all real numbers. Okay. So what can we do with that? Well, to be honest, we don't tend to use these graphs very much. We tend to turn the questions back into things in terms of sine and cos, all right? But we can do anything that we can do with other graphs. So, for example, if we sketch the graphs of 4 cosec and y equals x, well, 4 cosec is a graph transformation of the cosec graph. So we can do graph transformations with these graphs as well. We know we can do graph transformations with any function. Well, guess what? Just because we've got some new functions, nothing's changed there. We can still do those graph transformations. If we want to know where this function and this function meet, or if we want to know when these things are solved simultaneously, then we look at where the functions meet. And if they don't meet, then there's no solutions to those simultaneous equations. Okay, so if we want to know where any two functions are solved simultaneously, we just draw the graphs and look at where they cross. Well, if they don't cross, no simultaneous solutions. So everything we could do with any sort of graph that we've done before, we can now do with these graphs. So 1 plus sec of 2 theta, well, I know what the sec graph looks like. The 2 theta is a transformation, a sort of inside the brackets kind of a transformation. The plus 1 is an outside the brackets transformation, so we get a slide and a shift. So it slides to the left and shifts up, okay? Sorry, no we don't. We get a squash and a slide, don't we? So the 2x is a squash in by a factor of 2 on the x-axis, and the plus 1 slides it up 1 unit on the y-axis. So exercise 6b is just getting used to drawing the graphs, thinking about how they work, doing graph transformations kinds of things with them, and playing around with them. So good luck with that. That's exercise 6b and section 6.2.